Everyone. Today we're going to continue discussing gases. And last time we went over some gas laws. We went over Boyle's law, Charles's law, and the combined gas law. And today we're going to talk about Avogadro's law, and that will lead us into something called the ideal gas law. So Avogadro's law states that equal volumes of gases measured at the same temperature and pressure contain equal numbers of molecules. So for this law, volume is equal to a constant times n, where n is the amount of molecules in moles. So if we rearrange this equation, we can set up a relationship between initial volume and initial amount to final volume and final amount. So V1 over N1 equals a constant, and that same constant will equal the final volume over the final amount. So we can just set the initial amounts or volumes equal to the final amounts and volumes. Now, down below, you'll notice a diagram where we have three different, I guess we'll call them cylinder. They're really round bottom flasks, and each one has a different gas. So the first one contains argon, the second one contains oxygen, and the third one contains nitrogen. Now, you'll notice that the quantity of gas within each bulb is 1 mole. And then the pressure of each bulb is 1 atmosphere. The temperature is also the same for each. It's 273 Kelvin. So you'll also notice up at the top, the volume of each gas is the same as well. 22.4 liters. So again, equal volumes of gases measured at the same temperature and pressure contain equal numbers of molecules. So this is something that's very particular to gases. If you have the same amount of different types of gases and they're at the same temperature and the same pressure, they will all have the same volume. Now you will notice that the one difference here is the mass. So if we look at a periodic table, we know that argon has a mass of 40 grams for every 1 mole. Oxygen has a mass of 32 grams for every 1 mole. And nitrogen has a mass of 28 grams for every 1 mole. So the masses are different for these three gases, but they still all have the same volume if they're at the same pressure and temperature. So remember, gases, we said, are really energetic, which means that they're constantly in motion, and we're assuming that the particles of the gas are all really far apart. So it doesn't really matter what the mass of each gas is, because each gas is still going to fill the container that they're in. So the volume will end up being the same. Now, the temperature and pressure that we saw on the last slide, so the pressure was 1 atmosphere and the temperature was 273 Kelvin. Those are what we call standard conditions. So we abbreviate that as STP, which stands for standard temperature and pressure. So actually, if you have 1 mole of a gas at standard temperature and pressure, that gas will have a volume of 22.4 liters. So that's stated down here. So 1 mole of any gas, it doesn't really matter which gas we're referring to, will have a volume of 22 0.4 liters at standard temperature and pressure. So again, let's say we're using argon, nitrogen, and oxygen gases, and we're going to fill up separate balloons with each of those gases. So let's say we fill in one balloon with argon, one balloon with nitrogen, and one balloon with oxygen. Now, let's say we put 1 mole of each gas into these balloons. They're going to each take up 22.4 liters of space if they're all at 273 Kelvin and 1 atmosphere. And this is what we call the molar volume at STP. So each of these balloons will have a volume of 22.4 liters. So again, this is very specific to gases, but you'll notice that we wrote an equality down here. We can now use that as a conversion factor, as long as we're at standard temperature and pressure. So this can make calculations between amount and volume really easy. So let's do an example where we use the equation V1 over N1 equals V2 over N2, so that we just get some practice with that. So that's Avogadro's law. So let's say a gas is in a cylinder with a movable piston, like some of our previous examples. And initially, there are 0.5 moles of gas with a volume of 50 milliliters. Some gas leaks out of the cylinder. If only 0.3 moles of gas remain, what is the new volume of the gas? So this is a very small cylinder, apparently. That might have meant to be liters, but that's okay. So our initial amount of gas, so N1, is 0.5 moles. And the initial volume is 50 milliliters. And then we said that some gas leaks out of the cylinder. So at the end, only 0.3 moles of gas remain. So that's N2, our final amount. And then we don't know what the new volume is, so we're going to have to calculate that. All right, so let's plug in our values here. So V1 was 50 milliliters. N1 is 0.5 moles. We don't know what V2 is, so we'll just leave that as an unknown variable. And then N2 is 0.3 moles. Okay, so now we just need to do some rearranging. So we're going to multiply both sides by 0.3. So that will cancel on the right. All right, so now V2 is equal to 50 milliliters times 0.3 moles divided by 0.5 moles. So if we cancel units, we can see that moles will cancel and we'll be left with milliliters, which is good because we're calculating a volume. And when we plug this into our calculator, we should get a value of 30 milliliters. And that makes sense, right? Gas leaked out of the cylinder, so we would expect that the volume would decrease if we have less gas. And we can also see that from the initial equation that we had written out, so V equals Kn, which tells us that volume is directly proportional to the amount of gas that's present. All right. Now let's do another practice problem. This time, we're going to use our molar volume of the gas at standard temperature and pressure. So a gas at standard pressure and temperature, STP, has a volume of 33 liters. how many moles of gas are present. Okay, so it doesn't really matter that we have a particular temperature and pressure for this problem, because at standard pressure and temperature, we know that 1 mole of a gas takes up a volume of 22.4 liters. So we can use that equality as a conversion factor. So let's start with what we're given. We have 33 liters as our volume of gas. And then, because we're at standard temperature and pressure, we can just plug in the different sides of the equality up above into our conversion factor. So we want to end up with moles of gas. So let's put 1 mole in the numerator. And then we want to cancel units of liters. So let's put 22.4 liters in the denominator. Okay, so the units of liters will cancel and we'll end up with moles. And then 33 divided by 22.4 should give us 1.47 moles. All right, so if the volume of a gas at standard pressure and temperature is 33 liters, that means that we have 1.47 moles of that gas. And again, the identity of the gas doesn't really matter here either, because the gas particles are so far apart that even if the mass is pretty large or pretty small, it's still going to take up 33 liters, and we'll have 1.47 moles of that gas. Okay. Now, this is going to lead us into something called the ideal gas law. The ideal gas law allows calculations to be done in which the amount of gas varies, as well as the temperature, pressure, and volume. So mathematically, the ideal gas law is written as pressure times volume equals the amount of gas times this constant R times temperature. So what is that gas constant R? So we're going to call R the universal gas constant. And for our purposes, we're going to use the value of 0.0821 liters times atmospheres over moles times Kelvin. That's going to be our universal gas constant. Now, you can express this gas constant in different units, and that will change the value of the gas constant. So for instance, let's say instead of units of atmospheres, we wanted to use millimeters of mercury. I believe the value for that is 64.2 liters times millimeters of mercury over moles times Kelvin. So, if you change the unit there, that will also change the constant, but we're just going to use the one that's given here. So the ideal gas law is great if you're trying to figure out, for instance, the pressure of a particular gas, the volume of a particular gas, and maybe you don't have an initial value and a final value, you just have a certain volume or pressure of a gas. So you can solve for anything really using this equation. So you could solve for volume, you could solve for pressure, amount, temperature. That value of R, though, will always be a constant, and that's just a value that makes both sides of this equation equal to each other. Now, because we're using this particular value of R, we have to make sure that all of our other variables have the same units. So for instance, volume should always be in liters, pressure should be in atmospheres, N, the amount of gas, should be in moles, and temperature should always be in Kelvin, which we already stated previously. And that's because Kelvin is always positive. Okay. So let's do a couple of examples using the ideal gas law. And really, once you kind of figure out the values for each variable, it's pretty easy to use this equation. So example 1, a 2.5 mole sample of gas is confined in a 6.17 liter tank at a temperature of 28 degrees Celsius. What is the pressure of the gas in atmospheres? All right, so let's kind of break down what we're given here. So we're told that we have a 2.5 mole sample of gas. So that's our amount, N. And we always want N to be in units of moles, so this is already set. And then we're also told we have a 6.17 liter tank, so that's our volume. All right, and that's the correct unit we want. And then we're also told the temperature is 28 degrees Celsius. But remember, we want our temperature to be in Kelvin. So let's add 273, and that will give us a temperature of 301 Kelvin. Okay. All right, so now we're going to use the ideal gas law, where PV equals nRT. And we're solving for pressure. We were not given pressure. So if we rearrange this equation to isolate pressure, we just need to divide both sides by volume. So we'll end up with nRT over V. All right, so let's just plug in everything that we were given. So N is 2.5 moles. R is 0.0821 liters times atmospheres over moles times Kelvin. So that's a lot of units there. And then temperature we said is 301 Kelvin. And we'll divide all that by the volume, which is 6.17 liters. All right, now let's try to cancel some of these units. Make sure we're going to end up with atmospheres, which is our unit of pressure. So you'll notice that moles will cancel because the moles in the gas constant are in a denominator, and then the moles for the 2.5 moles are in the numerator. And then the same logic works for canceling Kelvin. And then we do have units of liters in the numerator and the denominator here. So those will cancel as well. So we should end up with atmospheres. Okay, so we're going to multiply 2.5 by 0.0821 and 301. And then we're going to divide by 6.17. So when we plug this into our calculator, we should get a value of 10 atmospheres. And I used 3 sig figs there because all of our values have 3 sig figs. So not too bad, right? You really just identify each of your variables, so which ones have values associated with them, which one are we solving for, and then we plug in everything that we know. And then here are the solution slides. And let's do one more ideal gas law calculation example. So in this example, a 4-gram sample of gas is found to exert a pressure of 1.71 atmospheres when confined in a 3.6 liter container at a temperature of 27 degrees Celsius. What is the molecular weight of the gas in grams per mole? Okay, so we're told that we have a 4-gram sample, but that's not in moles. So let's hold off on that for a little bit because we do want the amount of gas to be in moles. We're told the pressure is 1.71 atmospheres. We're told that the volume is 3.6 liters. And we're told the temperature is 27 degrees Celsius, but remember we want that in Kelvin. So let's add 273. And that gives us a temperature of 300 Kelvin. All right. So we do actually have all of our variables except for n. We don't know what n is. So let's solve for n, and actually we were asked what is the molecular weight of the gas in grams per mole. And we were given the amount in grams, but we don't know how many moles we have. So this works out. We're going to solve for moles, and then we'll use the 4 grams and the number of moles to solve for molecular weight. Okay, so let's write out the ideal gas law, PV equals nRT. And this time we're solving for n. So we need to divide both sides by RT. And that tells us that n is equal to PV over RT. Now, one thing to keep in mind, I often see people flip this expression where RT is in the numerator and PV is in the denominator. Don't make that same mistake because I see it a lot and you always get the wrong answer. So just make sure you're solving your equations or setting up your equations correctly. Okay, so let's do this calculation here. So the amount N is equal to the pressure, 1.71 atmospheres, times the volume, 3.6 liters, divided by the gas constant, 0.0821 liters times atmospheres over moles times Kelvin, and then temperature, which is 300 Kelvin. All right, so let's cancel some units here. So let's see, atmospheres in the numerator cancels with atmospheres in the gas constant, that's in the denominator. Liters cancels with liters. And then if we just focus on the denominator, Kelvin from our temperature will cancel with Kelvin in the gas constant, because that is in the denominator of the gas constant. And then we're left with 1 over moles. So let's kind of write that down here. So we have 1 over moles in the denominator. So we actually have 1 over moles. And what that tells us is we actually have moles in the numerator. So if you have a unit that's in the denominator of a denominator, it's actually in the numerator. So that works out because we do want to end up with units of moles. Okay, so when we plug this into our calculator, we're going to multiply 1.71 by 3.6, and then we'll divide that whole thing by 0.0821 times 300. So the value we should end up with is 0.250 moles of gas. But remember, we're trying to find the molecular weight of this gas. And I'm just going to make some room down here for the last step. Okay, so the molecular weight is equal to grams per mole. So we're going to plug in the 4 grams that we were told about earlier. And now we can divide that by the amount of moles that we just calculated. And 4 divided by 0.25 will give us 16 grams per mole. So that is our molecular weight of the gas. So we can use the ideal gas law in a lot of different ways. So for instance, here we used it to solve for the molecular weight of the gas. And there are many other examples where we can use the ideal gas law to solve for something that will then help us solve something else. And here is the set of solution slides. Now, one last thing before we end the video here. Now, the ideal gas law refers to gases that are quote-unquote ideal. Now, ideal gases are gases that are small, they're really far apart from each other, they don't interact with each other. So, for instance, they don't have attraction for each other. But unfortunately, ideal gases don't really exist. Real gases deviate from the behavior predicted by these gas laws that we just went over. But under normally encountered temperatures and pressures, those deviations are really small. So that means that we can use these gas laws, but they're actually estimations more so than the actual values that we would find for these gases. Okay, so in an ideal gas down below, again, these gases or ideal gases won't have any attraction for other gas molecules. And additionally, they're going to be really, really small. And then when they collide with something, they have what's called an elastic collision. So they're not going to, for instance, stick to another particle when they collide with it. They're just going to bounce off. Kind of like if you've ever played pool, the billiard balls just bounce right off of each other. But real gases do have some attractive forces that exist between molecules or particles. So you can see here there's some attraction between this gas molecule on the bottom and the gas molecules surrounding it. So that is not ideal behavior because we could potentially have some interactions between those gases, which could affect the pressure or maybe the volume of the gas. Maybe it affects the energy of the gas, which would affect the temperature of the gas. So again, these are really, really small interactions if they do occur. So the ideal gas law still gives us a really good idea of, for instance, the pressure or the volume or whatever we're solving for. But just keep in mind that ideal gases don't actually exist. And so this is more of an approximation. All right, so next time we're going to go over the last couple of gas laws, which have to do with partial pressures of gases. What do we do if we have a mixture of gases? And then also, what happens if a gas is diffusing out of a container? So we'll talk about all of that in the next video. I will see you there.